Before I talk about voltage and current, I thought it would be a good idea to briefly review a couple of terms here. First one is what a coulomb is. And a coulomb is simply a certain quantity of charge. In fact, we abbreviate charge with a Q because of it's representing a quantity of charge. And that number is 6.24 times 10 to the 18th charges, whether they be electrons or protons. That would be 1,000, million, billion, trillion, quadrillion, 6.24 pentillion charges is what 1 coulomb is. So there's that many electrons per 1 coulomb. And if we take the reciprocal of that number, we get 1.60 times 10 to the negative 19th. That'd be how many coulombs there are per 1 electron. That's the charge of a single electron. And then the other term we want to discuss here is what 1 joule is. A joule is a unit of energy, and energy is the ability to do work. So if an object has 1 joule of energy, it has the ability to do 1 joule of work. Work was defined as force times distance. So it would we would do 1 joule of work if we lift a 1 Newton weight up a distance of 1 meter. All right, we're going to discuss the first thing we need to do is look at what is the differences between electrical potential energy and just what electrical potential is. Same term, but just leaving off the word energy has a different meaning. Now, as we discuss voltage, it seems to be very important to connect back to our understanding of gravity and gravitational potential energy. So if I have a 2,000 Newton crate and I lift it up a distance of 15 meters, force times distance, you just did 30,000 joules of work. And it takes energy to do work, so the crane must have lost 30,000 joules of energy in giving the crate 30,000 joules of energy, or in doing 30,000 joules of work on it. The crane lost that in terms of the chemical potential energy in diesel fuel. So the work that we did is going to be the change in the gravitational potential energy, and U for potential energy. So 30,000 joules. All right, just kind of put it in general here. This crate has mass, and it is gravitationally attracted to this mass. And if we pull those two masses away from where they want to be, this mass is going to be wanting to sit right there on the surface because of the attraction. Separating two things that are gravitationally attracted to each other give them gravitational potential energy, and that would be measured in joules. So the comparison here is if we had a spring, and a very heavy spring, and we stretched that spring, while the spring is in the stretched state, it has spring potential energy. As soon as you let go of it, it can snap back and do work on whatever it is touching. Now, that was gravitational potential energy. Electrical potential energy is very similar, except these charges are repelling that charge. They're pushing it away. So if we take that charge and push it to where it doesn't want to be, it took work to do that. And we've given it energy, also measured in joules. So electrical potential energy is just doing work on charges, giving them energy, pushing them to where they don't want to be. It's kind of like taking the spring here, and instead of stretching it, we're going to compress it. While it's in the compressed state, it would have also spring potential energy. Typically, we have a bunch of positive charges here and a bunch of negative charges here. Opposites attract, so this thing really wants to be here. It really doesn't want to go over there. So if I did work on it and I pushed it from there to there, It's like taking two springs and it's compressing going that way and stretching going that way, but we're giving that charge lots of energy. Now back to our analogy with gravitational potential energy. Each one of these masses is 1 kilogram and it weighs about 10 newtons. So if I lift 10 newtons up 1 meter and another 10 and another 10, I have just done a total of 30 joules of work. I've just given it 30 joules of gravitational potential energy. Now we're going to introduce this term. That was 30 joules total, because each one was 10 newtons lifted 1 meter. 30 joules total, but that was only 10 joules per kilogram. Each of these weighs or has a mass of 1 kilogram. So that is called just gravitational potential. It's not the total amount of energy, it's how much energy there is per kilogram. If I take these 10 newtons and I lift them up now 2 meters, each one has done 20 joules of work, 60 joules altogether. So that's gravitational potential energy. But the gravitational potential is just how much energy there is per kilogram. Gravitational potential. So electrical potential energy is the total amount of energy these charges have, which is equal to the total amount of work done in getting them to that location. It's measured in joules. Electrical potential, leaving off the word energy here, is how much energy there is for each coulomb of charge. And that would be measured in joules per coulomb. Electrical potential energy is just how much energy there is per charge. And there is a common unit for these two units. Joules per coulomb is the same thing as volts. Okay, so volts. And there's another name for electrical potential. It's called voltage. So voltage is measured in volts. Okay, another name for voltage is electrical potential, and volts is the same thing as how much energy there is per quantity of charge. It was named after Alessandro Volta. So if we had a 1.5 volt battery, it just simply means that there's 1.5 joules of energy for each coulomb of charge that's packed into that battery. Now, this is kind of repeating what I was saying, but voltage is the electrical potential energy. And just like we did with gravity, potential energy was abbreviated with a U. U sub G would be the gravitational potential energy, but U sub E is the electrical potential energy. So it's how much energy there is per charge, Q for charge, and that was because it was a quantity of charge. And that's what voltage is. Same thing as electrical potential. All right, so if we have a battery here, and right now the battery is dead, there's no voltage on there whatsoever, these terminals are going to have no net charge. There'll be an equal number of positive and negative charges on there. So if I want to now begin to charge this battery, I've got to do work on those charges. I got to take an electron and push it right over there to that place there. And it's going to take a little bit of work to do that because there's now a net charge there. If I push another one over there, that was actually harder to push because there's now a net negative charge and it's repelling the negative charges over here. Similarly, there's a net positive charge on this side. So as I push an electron over here, it's being attracted back to here and repelled from over there. But if I moved, let's say every one of these little charges represent a coulomb worth of charge. So that's not just a single electron, that's a bunch of electrons. And if I moved over 2 coulombs of charge and did a total of 5 joules of work to do that, the voltage on the battery right now is how much energy there is per charge. That'd be at 2.5 volts. Now, if I pushed another charge over here, it's not going to be linear here because it was harder to push that third coulomb over than it was the second. Let's say that I did a total of 12 joules of work to push over the 3 coulombs of charge. So the battery is now at a voltage of 4 volts. And now it's getting harder. You got to kind of put your back into it. And the more charges we push over, the harder and harder it becomes. And so it's really getting really hard. We got to do a lot of work to get them over there. And by the time it's almost fully charged, that charge really doesn't want to go. We got to get a lot of help to push really, really hard to get that charge over there. So if by the time we have this charged, we've done a total of 84 joules of work to push over 7 coulombs of charge, joules per coulomb, you divide those two, and you get 12 volts. Now, once those charges are separated, they're still highly attracted to over there. So if I give them a path to follow, these electrons are going to flow through the filament of the light bulb and come back into here. And as they flow through there, there's resistance, and that resistance causes heat and light and makes the light bulb go. Now you might ask, okay, so what is the little guy inside that battery that's doing work? Well, there's 2 ways. Inside the battery, there's usually lead plates. There's 2 different metals in there. And then there's usually some acid, like hydrosulfuric acid. And there's a chemical reaction between the acids and the metals that are pushing electrons from one side to the other. In a generator like this, when charges move in a magnetic field, there's a force put on those charges. And that force is this guy here. My video on magnetic force would be a good one to watch to understand that. If I have a AAA battery and it's at 1.5 volts, there's about 3,600 joules of energy contained in that thing, and about 2,400 coulombs of charge that ultimately goes through the battery as the chemical reaction takes place. But if you take that many joules divided by that many coulombs, you get 1.5 joules per coulomb. A 9-volt battery has a little less energy and a lot less charge, but that much energy divided by that much charge is 9 volts. A big lantern battery like this, 96,000 joules of energy, 16,000 coulombs, and if you take joules per coulomb, you get about 6 volts. All right, so that was just an introduction to what electrical potential was, or voltage. Now I want to look at what electrical current is. And electrical current, it's always helpful to think about it as it's like water flowing through a pipe or water flowing through a river. But to measure the flow of a river, we use cubic feet per second, CFS. It's a quantity of water flowing by every second. So if we had a reference point here, and if we had 12 cubic feet and 12 cubic feet and 12 cubic feet, if 12 cubic feet flowed by that spot every second, that would be quantifying the flow of that river. Flow is not the same thing as the velocity, because if that river were wider, it could have 12 cubic feet, 12 cubic feet, 12 cubic feet, still getting the same quantity of charge flowing by every second, but it's just flowing at a smaller velocity. So the Mississippi River flows at about 500,000 cubic feet per second on average, while Clear Creek in Golden, Colorado typically flows at about 450 cubic feet per second a lot more exciting ride, and faster, but it's not nearly the flow. So let's see if we can think of what units would be appropriate for electrical current as all these charges flow through the circuit, or flow through the wire here. We want to be able to quantify the current. Well, the units are going to be similar to what it was for water. It was a quantity of water flowing by every second, so it's going to be a quantity of charge flowing by every second. So coulombs is our quantity of charge, and it's how many coulombs go by every second. And there is a common unit. Coulombs per second is the same thing as amps, and it was named after Andre Ampere. And if we have in a circuit or through a wire 12 amps, that means there are 12 coulombs of charge flowing by a point every second. That doesn't sound like a lot, but if we understand that a coulomb is 6.24 times 10 to the 18th electrons, there's 12 times that flowing by every second. There's going to be, 1,000, million, billion, trillion, quadrillion, 74.88 pentillion electrons flow through that wire every second when there's 12 amps of current in that wire. So current is how many coulombs go by every second. Okay. We use I for current, and students tend not to like that. It doesn't seem to make sense to them, but it is based upon the phrase intensité de courant. I think it's something very similar to that. It's a French phrase, which means the current intensity. So we're talking about the intensity of the current. So I for current, Q is for charge, but it was a quantity of charge, and T, well, that stands for time. And that students tend to like. All right, so let's say this is a real thick wire, and this is a thick wire tapered down into a smaller wire. So if we had current running through this large one here, or we had current running through it here, the current that goes by here must equal the amount of current that goes by there. Because if we count how many charges go by here every second, all those charges are also going by there every second. Now, it's more difficult for electrons to flow through this smaller diameter wire than it is to here. So there's going to be more resistance in this wire, which slows down the current. But not only does it slow it down here, it slows it down everywhere, because we can't have a less amount of current here than here. The charges don't disappear. Just however many charges are going by here every second must be the same here. If we didn't have that constriction, if it was just a big wire the whole way, then there'd be more current running through that wire altogether. But that's just a little introduction to current. Now, when we have batteries, and they indicate what the capacity of the battery is, that was 5,000 mAh. That's milliamp hours. And it's kind of funny here, 5,000 milliamp hours. A milliamp is a thousandth of an amp. So 5,000 thousandths of an amp is the same thing as 5 amps. It would have been easier just to say that was 5 amp hours. I think it's a marketing ploy where that looks like, wow, 5,000 thousandths of an amp hour. So if I had a drill here that's on a battery pack, and that says it is 2.6 amp hour battery, This is a variable speed drill. So if I pull that trigger lightly, it's going to use just a little bit of current. If I pull that trigger harder, it's going to use more current. So if I pull that trigger just hard enough to use 3.2 amps, how long will that battery last? So if it is a 2.6 amp hour battery and I'm using only 1 amp, the battery is going to last 2.6 hours. If I used 1.3 amps, the battery is going to last, I'll pause there for you to think, but you are correct, 2 hours. If I really pull that trigger hard and use 2.6 amps, the battery is only going to last 1 hour. So back to the original question, how long would the battery last if we pull the trigger to use 3.2 amps? Well, we can use dimensional analysis and amp hours divided by amps. Amps would cancel and it would give us that many hours. I think I will stop there and do more next time with Ohm's law and resistance.